One way to describe functions is using concavity. If you're ready to learn about it, click here. Great, let's get started. A function is said to be concave up if it's smiling. Here's an example. Notice that this function has a smiling shape to it. It's curving upward. On the other hand, a function is said to be concave down if it's frowning, like this function here, which curves downward. Take a look at this function. Would you say it's part of a smile or part of a frown? In other words, is this function concave up or concave down? Right, this function is concave up. Here are a few examples of functions that are concave up. The middle function is a complete smile, and the left and right functions are parts of a smile, but all of these functions are concave up and curve up as x increases. And here are some similar examples of functions that are concave down. They all curve downward as x increases. Now functions can be concave up or concave down in different places. For this function here, at which points is this function concave up? Precisely. So the left part of this function is frowning, meaning it's concave down. And the right part of the function is smiling, so it's concave up. Now here's another function. At which of these points is this function concave down? For this function, the left part is concave down and the right part is concave up. Now there's a point in between where this function switches concavity, meaning on one side it's concave up and on the other side it's concave down. Places where functions switch concavity are called points of inflection. Here's a function that switches concavity a few different times. Which of these points are points of inflection? In other words, where does this function switch from concave up to concave down or concave down to concave up? Great work! So far we've been looking at a lot of curvy functions. What about straight lines? Do you think a straight line is concave up, concave down, or neither? Now it's time for you to make your own function and see where it's concave up or concave down. To make your own function, drag anywhere on this graph. Regions that are concave up are shown in green, and regions that are concave down are shown in red. And points of inflection, which occur between the concave up and down regions, are the black dots. Here's your final challenge. Try making a function that's concave up most of the time and has at least 3 points of inflection. Let's introduce 2 more types of functions, odd and even. Numbers can be odd, like these numbers here, or even, like these numbers. But when we say a function is odd or even, we mean something quite different. If you're ready to learn about odd and even functions, click here. If you already know about them, then which of these functions are odd? Okay, let's start with odd functions. Here's an example of an odd function. A function is odd if, when you rotate it 180 degrees around the origin, you get the very same function. Let's pick a specific point, like this one over here, that we can keep track of during the rotation. So if we now rotate this function 180 degrees around the origin, we see that we get the original function again. Let's see that one more time. Notice the shape of the original function. When we rotate it 180 degrees around the origin, we get exactly the same shape again. That means this function is an odd function. Now, which of these other functions would you say are odd functions? Right, if you rotate this first function 180 degrees around the origin, you get the same function again. So this function is odd. If you rotate this second function 180 degrees around the origin, you get a different function. So this function is not odd. The third function here is odd, and the last one is not. Now that you know how to identify which functions are odd, let's take a look at even functions. Here's an example of an even function. A function is even if it's symmetric across the y-axis. So on either side of the y-axis, the 2 halves of this function are reflections of each other. Take a look at these functions here. Which ones are even? Nicely done. Now let's look at a few power functions. Here are the graphs of y equals x to the first, y equals x squared, y equals x cubed, and y equals x to the fourth. Which of these functions are odd? Exactly. When x is raised to an odd power, like 1 or 3, you get an odd function. So that's why functions with this kind of rotational symmetry are called odd functions. And if you look carefully at the even powers, you'll see that they're even functions. Because even powers are symmetric across the y-axis, functions with this kind of symmetry are called even functions. Let's see if we can come up with a rule that describes even functions. Here's an even function, and let's call it f. Let's take a look at an x-coordinate, like this one over here, and let's call it a. So the height here is f of a. If this function f is truly even, then what else must f of a be equal to? If you're not sure, then click down here. Okay, no problem. Let's figure this out. At which other point does this function give you the same value as it did over here, f of a? Right, at these two locations, this even function has the same value. And this point over here is the same distance from the y-axis as this point, but in the opposite direction, meaning this x-coordinate is minus a. So if this function really is an even function, then the y-coordinates of these 2 points should be equal. So f of a equals what? Exactly. So for this function to be even, f of a had better equal f of minus a. The general rule for even functions is that f of x equals f of minus x. If the function f is even, then this equation must be true for every value of x. So that's the rule for even functions. Now let's find the rule for odd functions. Here's an odd function. Again, let's look at an x-coordinate and call it a. So this y-coordinate is f of a. If this function really is an odd function, then what else must f of a be equal to? If you're not sure, then click down here. Well done! If this function is odd, then f of a had better be equal to minus f of minus a. So for a function to be odd, f of x equals minus f of minus x for every value of x. You'll often see this rule written in a slightly different way. First, let's just flip the sides of the equation. And if we divide both sides by minus 1, we can move the minus sign over to the other side. So this is another way to write the rule for odd functions. F of minus x equals minus f of x. Here's a quick recap. If a function is odd, that means f of minus x equals minus f of x. If this equation is true for all x, then that's actually the precise definition of an odd function. Here's an example of an odd function. If you rotate it 180 degrees around the origin, you get the same function back. This is only true for odd functions. And if a function is even, that means f of minus x equals f of x for every input x. This is the definition of when a function is even. Here's an example of an even function, and all even functions are symmetric across the y-axis.